Yes, thank you. My name is Chase Norman. I'm going to talk to you today about Canonical, which is an automated theorem prover for dependent type theory. When we think about proof automation in dependent type theory, we think about a pretty fragmented landscape of tactics. For instance, if you have a problem that's in the first order fragment, you can use a first order reasoner to prove those theorems. If you have a problem that's about linear equations, you can use a linear equation solver. Or if you have a decidable theory of some kind, you can use a decision procedure. But I think it would be desirable to have some kind of system that has general reasoning capability across the system so that you have at least some level of ambient capability to solve regardless of what your theory is that you're reasoning about. So there are a few design requirements for such a system. First of all, it has to be able to support a sufficiently expressive theory. In this case, we're looking at dependent type theory. It should be able to reason about, just like a human is able to reason about, all of dependent type theory. And importantly, it should be able to generalize and reason about theories that it has never seen before or that it's never been specifically programmed to reason about. And thirdly, it should be able to provide readable proofs. I think once you give up the constraint that you want to provide readable proofs, you give up the constraint of reasoning as a human would reason, because you're no longer constraining that it produces a certificate that reasons as a human would conduct their argument. So I'm introducing a tactic called Canonical, which is available in Lean, and I'm going to give a demo now. At least I think I am. All right, so here I have a Lean project. How much larger? More? This one? One more? Oh my goodness. Yes, yes. We're going to use it one time and then it's going to go away. So I don't have Canonical installed here. There we go. So Canonical is not installed. We're going to go ahead and install it. This is the Canonical Lean repository here, and it has this nice instructions for how to install it. We can go to our Lake file, and we can add the requirement for Canonical, and then we can do Lake update Canonical. This will install it. I see many of you are on your laptops. Maybe you can follow along. And then we can restart the server and restart the file. Suspenseful. Okay, just like that, we have Canonical installed. It's starting to prove some things, but we're going to start here at the bottom of the file and let it catch up to us. So yeah, Canonical is a tactic in the Lean Proof Assistant. You can invoke it using Canonical, the syntax, and then you can provide it a list of premises. So in this case, we've given it a premise that a proposition cannot be equal to its own negation, and we've given it a premise that if a function is equal on all values, then if a function is equal on all arguments, then the two functions are equal. And so we're trying to prove Cantor's theorem, which is the statement that if you have a function from x to the power set of x, then f cannot be surjective. And so Canonical has provided this proof certificate here for us, so we can paste that into our file, which uses the premises that were given. And also, I want to highlight here this argument, which is actually the Cantor diagonal set. So here we have FAA, which is the diagonal, implies false. So this is a higher order argument that's supplied by Canonical, which is the construction of the Cantor's diagonal set. Here's another example. So we have a group G, and we'd like to construct multiplicative homomorphisms from G to itself. And so this time we're asking Canonical not for one inhabitant, but actually two inhabitants of this type. And we are providing the premise that 1 times any element in a group is equal to itself. And so Canonical is providing us two suggestions here. The first says this is the identity function and provides the proof by reflexivity. And the second is the unit the function that sends all elements to the identity element, and the proof is using that premise that we said before. So we can construct, these are actually both trivial endomorphisms that a group has. This was an example that was written by Patrick Massot. It is from Analysis, and it's saying that continuous functions are sequentially continuous. So we have a delta epsilon definition of continuity, and we have a notion of a sequence tending to something on the real numbers. And we have this theorem that uses these definitions to prove this result. And Canonical is able to reason about these definitions, reason about the existential quantifiers and the universal quantifiers and the less than or equal to and all of that, and produce this proof certificate, which does involve synthesizing functions in some cases. This is an example theorem from MathLib about complete lattices, which says that the supremum of S intersect T is less than or equal to the supremum of S met with the supremum of T in a complete lattice. And the interesting about this is that supremum, in some sense, is higher order because it's over a set, and a set in Lean is a function. And Canonical actually provides the exact theorem that's written in MathLib. So this is the same implementation of the MathLib proof. And again, it's able to synthesize functions and generally perform higher order reasoning when it's required to. Another interesting aspect of Canonical is that it's able to reason constructively, and importantly, it's able to generate programs, not just proofs. So here we have a definition of vectors, which are essentially lists, but they have a length. So they can either be nil, which is the empty vector, or cons, where you add a new element to the vector, and it will append one element to this vector of length n to create a vector of length n plus 1. And so then we can ask Canonical, if I give you a vector of length n and a vector of length m, produce for me a vector of length m plus n. And it will synthesize this recursive function that starts with the vector v2 and then performs cons on the sort of inductive hypothesis vector with elements from vector v1 until it produces a vector of length m plus n. So this is synthesizing the append function given a type specification. And then for my grand finale here, yes, go ahead. Do you have a suggestion for which function would be synthesized instead?
So it happens to work because append is the only reasonable function of that type?
Yes, so the question was, why did it synthesize append as opposed to some other function? And the reason is because the typing constraint is sufficiently constrained that this is the most reasonable implementation for a function of this type.
Right, but at least there's a version where I append the other way around, right?
Yeah, so if you flip the sides that these addition is on, so I can do n plus m instead, and then I can have Canonical run on this. Oops, Canonical. Then we can get an append that goes in the other direction. So this time we have v1, and v2 is what we're recursing over. So, and then also if you provide like add com or something like the commutativity of addition, maybe you could ask it even for multiple, like I showed before. You can ask it for multiple implementations of the same function, and you can choose which one you'd like. So yeah, the idea is use your types as strongly as possible in order to constrain your generation. But then if you need to generate more than one, you can always do that. Yeah. And so this is my final example here. We have a custom definition of the natural numbers, nat prime, which is either 0 or the successor. So this is the standard inductive definition of the natural numbers. And I've also given the standard definition of addition on the natural numbers, the same that's used in the standard library. And now we ask to prove the commutativity of this addition function. So we want to show that add AB is equal to add BA. And so Canonical produces this proof. So if you've ever tried to prove the commutativity of addition on the natural numbers, you know that it's usually a multi-step process. First, you prove that 0 plus n is equal to n for all n. That's an induction proof. Then you prove that the successor of n plus m is equal to the successor of quantity n plus m. That's also an induction proof. And finally, then you can do a third induction to prove that addition is commutative. Now, Canonical does all three of these at the same time. So here you can see we have three instances of the recursor on the natural numbers, which is induction. We're synthesizing the induction predicates, and the induction predicates are higher order, right? They're functions. And we're synthesizing the proofs inside. Now, Canonical is reasoning about equality in this case, but Canonical actually doesn't have any specialization for reasoning about equality. So it's actually using the recursor on equality in order to reason about equality and synthesizing motives for those recursors as well. So there's a lot going on in this proof, including some calls to simp, which I'm not going to explain at this point, but you can attend my talk on Thursday if you want to hear more about how that works. Okay, but I want to move on and talk about how this, what this all means, because I'm sure you're all very curious. So how does this work? So in Lean, we have a goal type, which is an expression. And what Canonical, the tactic, does is it converts this expression into a type in our custom dependent type theory, which we send over the foreign function interface to a program written in Rust, which is called Canonical. And Canonical takes types in our type theory and produces terms in our type theory that are of that type, which are then sent back across the foreign function interface, converted into a Lean expression, which is then presented to the user to be inserted into the file. Okay, so let's talk about what Canonical does. The problem is called type inhabitation, which is the problem of finding terms of a given type. So if you have a proposition, this is equivalent to theorem proving. If you have a function signature, this is program synthesis. And if you have a data type, then this is just finding objects constructively of a given data type. So why do we have our own dependent type theory? Well, this is Lean's internal representation of expressions. It has 12 constructors. It's rather complicated. Our internal representation of terms looks like this, which has one constructor. This is a structure type. So yeah, there's only one term constructor. And you can think of this term as being like this, with a lambda expression, with a list of parameters, a head symbol, and then a list of arguments. This is canonical form. It's beta normal and eta long. And there's only one way to represent a term up to definitional equality, and that's important for the behavior of our algorithm. Likewise, there's only one inference rule that you can perform, which is applying a head symbol to newly created arguments. And so there's only one way to construct a term. There's only one inference rule that you can perform to derive terms. And there's only one constraint type that's generated throughout the process, which are definitional equality constraints. And as I mentioned before, those are quite easy to work with. And so, if there's some key message from this is if you are very discerning about how you define your theory, then you're going to be richly rewarded. You're going to have algorithms that behave very nicely on those structures. Okay, so the operation in question, this inference rule that I'm talking about, is called refinement. So in the process of refinement, you start with one metavariable here, and you choose a head symbol for that metavariable, which creates new metavariables, and you recurse. You continually pick a metavariable, pick a head symbol for that metavariable, continuing until eventually you decide the head symbols for all the metavariables and you have no more metavariables left. And so I want to show a quick demo, if I can, of refinement. I have this flag here, plus refine, that lets you see what Canonical sees. So if we open up the info view here, this is what Canonical sees. It starts by having a single metavariable of a given type. So here we're trying to prove Peirce's law. So we're given double negation elimination. We're given this P, and we're trying to prove A. So if you don't know, Peirce's law is a statement that holds classically but does not hold intuitionistically. And so to prove this, we can either use double negation elimination, or we can just try to use P directly. This is not going to work. It's going to be an infinite branch. But double negation elimination is going to work. I'm actually going to turn off this autofill here. So when we call double negation elimination, there are two metavariables that are created. This one here only has one option. This one here has two options. It creates, that we have sort of a choice of what to work on next. We might as well click this one because it's the only option. Now we're trying to prove false now, so we're going to use this one instead of double negating on false. That doesn't make much sense. Now we can finally use our premise P. Okay, we have no choice but to double negate in order to produce B. We have no choice but to double negate on B. And then it's just a couple steps later before we've finished the goals. So we sort of have a structure editor here for Lean. You can just click around and you can create terms of a given type. Just as another example, here's Lever's fixed point theorem, which is actually a generalization of Cantor's theorem and many others like Gödel's incompleteness theorem and so on and so forth. And so now I have autofill. So it's filling in a lot of things that are forced moves automatically. But you can see there are a bunch of variables here that each have a small finite set of next possible head symbols. And the important thing to note is that these are all possible head symbols that are going to unify with the goal type. And they only consist of options that are reasonable continuations according to the typing rules of the dependent type theory. So yeah, I think this proof is as simple as just making a couple decisions, and then just like that, you've proven Lever's fixed point theorem. But I'm going to return to the presentation here. So the important thing to understand about our implementation of refinement is that we're only searching over canonical forms. So we're not searching over a bunch of redundant things that are the same term. We're only looking at options that are type correct with some notion of type correctness on a partial term. You can work on the meta variables in any order you'd like. So this is a very important idea. It would be very easy to work on the meta variables in the forward direction because that's the direction that dependency goes. So you could work on something before you work on something that it's dependent on. But an important part of our algorithm is being able to work on things that are on the rightmost side before we work on things that are the dependencies. And also it's complete. So we consider all possible options that fit our typing rules. So with this, we have a number of options for each meta variable in the problem that constructs a search tree. So what we do is we perform iterative deepening depth-first search to exhaustively search for terms of a given type. And because this is a search tree and you know the branches don't overlap, we're able to parallelize this. So we partition the tree into various independent segments, and we run them on all the cores of your machine. We have a highly optimized Rust program. It's got its own memory management and everything like that, and it's searching over millions of proof directions every second. So here are some important observations about the algorithm. So we need to choose which meta variable to work on in which order. How do we choose which meta variable to work on? Well, here's an example of two meta variables. We need to produce a natural number, and we need to produce a proof that that natural number is equal to 1,000. So you know, let's do the easy thing and just work on the easy one first, right? The natural number. Let's try 0, you know? If you try 0, then you'll find that it's very difficult to find a proof that 0 is equal to 1,000. You're going to time out, you're going to look, and you're not going to find anything. Okay, well, maybe 1's going to work, right? Let's try 1. So if you try 1, then again, you're going to find that there's a timeout. Okay, this doesn't seem to be working so well. So let's go the other way around. We're going to start by trying to prove the equality by reflexivity. And then that's going to create a definitional equality constraint that n needs to be equal to 1,000, which then makes it easy to immediately decide what n needs to be. So in general, the learning from this is that we prefer to work on the most difficult metavariables first, the hardest, rightmost metavariables first. Now this gets complicated in the presence of dependency, especially where you have undecidable unification and stuff like that. And you know, you can check the paper for more details, but essentially our algorithm heavily depends on the ability to propagate these definitional equality constraints and reduce them and glean as much information as possible from the definitional equality constraints. And then there's one final concept I want to talk about, which is the entropy metric. So I mentioned before that we do iterative deepening depth-first search, but we don't simply go to depth 2 and then go to depth 3 and then go to depth 4. Instead, we have a custom metric for the depth, which is called entropy. And so this is an illustrative example here of a tree that has one branch with a bunch of forced moves, right? Every choice, once you make that first choice, is forced along this rightmost branch, right? So in some sense, this right branch accounts for 50% of the probability mass, so to speak, of the tree. Whereas another branch over here, you know, an edge at the same depth level vertically only accounts for like 2% of the tree with respect to if you assume that everything is split evenly at each branch point, right? So we don't iterate by depth. Instead, we iterate by entropy, or by the percentage, by the number of decisions that you had to make and how many options there were for each of those decisions at each decision point. So in general, you expect to find a proof much more often down this path than you do down the paths that had a lot of branching options. Okay, we're essentially required to provide some sort of benchmark that demonstrates that we're doing good things. But the point I want to make about canonical doing well on the natural number game is that the difference is a qualitative one, not a quantitative one. So if you're unfamiliar, the problems in the natural number game involve proving elementary properties about the natural numbers, and often these proceed by induction. And so if you use a first-order theorem prover like Duper or a tactic search procedure like ASOP, you're simply not going to be able to perform induction-based proofs, right? And so the difference here is a qualitative difference. Canonical is able to reason with induction, do higher-order reasoning, and the like. But the real interesting thing about this benchmark is that Canonical has no native support for natural numbers or even equality or inequality or anything like this. These are not primitive notions in the search of Canonical. And so the capability of Canonical to reason about these things in this particular benchmark is indicative not just that Canonical has the ability to reason about the natural number game, but indeed any theory of similar complexity for which it hasn't seen before. It's this generalization that we're talking about. Okay, so why am I talking about this with all of you? So if you use Lean, I'd like to see you try out Canonical. That would make me very happy. But I want to specifically call out the folks that are using the other dependently typed proof assistants like Rock and Agda. I want to emphasize that Canonical is a standalone Rust program and does not have any direct relationship with the type theory of Lean. Almost all the code in this project is the Rust code, and there is some Lean code that performs the translation to our internal representation and back from our internal representation to solve goals in Lean. But I would like to see similar tactics written in the other dependently typed proof assistants along the same lines. So I'm looking for people who are well-versed in these other type theories to assist with the development of what I think would be the first tactic which is available across the dependently typed proof assistants. Okay, so I've left some time for questions. I'm sure you have a lot of them, so I'll take them now.